We will look now at the last classical type of combinatorics problems, combinations with repetitions, and we'll look at that with the example ice cream. Just a short reminder, we started with permutations and later we saw also permutations with repetition. The playlist is a permutation without repetition. We looked then also at variations with repetitions and variations without repetitions. And then we had the example combinations without repetition, namely the example werewolves. And now what is missing are the combinations with repetition. So here we go. We'll start with some ideas and then we'll come to the combinations with repetition. So example 1, we have a restaurant that offers 5 flavors of ice creams: banana, chocolate, mint, pistachio, and vanilla. And you choose now 3 scoops. And now we look at different situations. So, and always the question is, how many different possibilities are there? So in A, build a cone tower with the 3 scoops if the 3 have to be of different flavor. Here you see a sketch, you have the cone and the 3 scoops with the 3 different flavors. Well, obviously there are 5 times 4 times 3 different possibilities. We have 5 possibilities for the first scoop to choose. Then, since it has to be different flavor, only 4 for the second one and 3 for the last one. Question B is the same like question A, except for allowing several scoops being of the same flavor. Here you see it symbolized. And the result is obviously 5 times 5 times 5, since for each scoop we can choose amongst 5 different flavors. So 5 to the power of 3. Since we're building a tower in the first and in the second example, it is important in what order the different flavors occur. So red, then green, then red is different than red, red, green. And that's the same up here. And that's why these are variations. We're selecting 3 elements from 5, but the order matters. The same here. Here, additionally, we have repetitions. Here we have no repetitions. Task C is completely different. We don't make anymore a cone tower, but we just make a bowl with the 3 scoops, and we require all the 3 scoops to be of different flavor. Obviously, here the order doesn't matter. So the result is just 5 choose 3, which in the end is just 10. This is the combinations without repetitions case, and now we'll get to the combinations with repetition. We make again a bowl with the 3 scoops, so order doesn't matter, but there can be several scoops of the same flavor. So a bowl can, for example, consist of 2 banana and 1 chocolate scoop, or 3 pistachio scoops, or chocolate, pistachio, and vanilla scoop. To find now out how many different possibilities there are in this case, the idea is to describe the bowl differently, namely by using for a scoop a circle and delimiters, vertical lines, where the latter determine of which flavor a scoop is. Let's look at an example to get what is meant by this. This code here describes a bowl with 1 banana and 2 mint and no chocolate, no pistachio and no vanilla. Why is this the case? Well, we start with the bananas. There is a scoop there, a banana scoop. Then there is a delimiter, so what we see next are the chocolate scoops. Well, between this delimiter and the next one, there is no circle, so there's no chocolate scoop. After the next delimiter, we get to the mint. Well, there are 2 scoops here before the next delimiter comes, so we have 2 mint scoops. Then there is another delimiter, which means we are now at pistachio scoops. Well, there is none between this and the next delimiter. And at the end, after the last delimiters, are the vanilla scoops. Well, there is no vanilla scoop. If this was too fast, look at it again. I'll make now a few examples. I'll say stop, which means you should stop the film, reflect what you think, what type of bowl does this represent, then continue and verify if you understood it correctly. I guess that after the few examples, you'll get the idea. So here we go with the next example, and stop. And here is the result. The bananas are before the first delimiter, so there is none. Then after the first delimiter, we have the chocolate. There's 1 chocolate scoop. Then after the next delimiter, we have the mint scoops, 1 again. After the next delimiter, we have the pistachio scoops, another 1. And after the last delimiter are the vanilla. Well, there's nothing. And we continue with the next example. And stop. And here is the result. Again, before the first delimiter, no scoops, so no banana. After the first delimiter are the chocolate scoops. There are two of them. There is nothing after the next delimiter, which means there's no mint. After the next delimiter, we have the pistachio, again none. But after the last delimiter, we have one vanilla. And we continue with the next example. Stop. Well, there's nothing before the first delimiter, nothing after the first, nothing after the second. Only after the third we start with something, which means we are already at pistachio, and there are 3 pistachio, and nothing after the last delimiter, so no vanilla. So we see that each arrangement of the 3 circles and the 4 vertical bars, the 4 delimiters, corresponds exactly to one bowl, and vice versa, meaning each bowl corresponds exactly to one arrangement. So this means that the number of different possible bowls is exactly the same as the number of possible different arrangements. Well, how many different arrangements are there? Well, we have 7 elements, but 3 of them are the same, the 3 circles, and 4 are also the same, the 4 delimiters. So we have a permutation with repetition, 7 factorial divided by 3 factorial times 4 factorial, which is the same like 7 choose 3. And now the question is, where does 7 come from? Well, the 7 is the 3 scoops plus the 4 delimiters. And the 4 delimiters, this number of delimiters is just the number of different flavors, namely 5 minus 1. We need 1 less than we have number of flavors. So this leads to our final formula for number of combinations of k out of an element with repetition. N plus k minus 1, choose k. So n being the number of flavors, the 5 here, and the k being the number of scoops that we're taking. This is the 3. We're choosing here the 3. We're choosing k out of n elements. We're choosing 3 scoops out of 5 different flavors, and we can use the same flavor several times. What is important here is to note you have always to be aware which is the k. You are not allowed to use here n. Now read example 2 and let's solve A. It helps to reflect what are the flavors and what are the scoops in this example, and reflect for a moment before you listen to the solution. So stop the film now. Okay, so in this example, we have 3 flavors, namely John, Quentin, and Ramona. And the 25 students are actually the 25 scoops. Student 1 just chooses one of the 3 here, but I don't care if it's student 1 or which one. It's just 1 scoop of flavor John, Quentin, or Ramona. In the end, I'll have 25 scoops. We are choosing from 3 elements, John, Quentin, and Ramona, so n is 3, and we're choosing 25 times, so k is 25, and inserting that into the formula, we get 3 plus 25 minus 1, choose 25, means 27, choose 25, so the final result is 351 possibilities of results. Now look at task B, where the students are also allowed to leave the election leaflet empty. How many possible results are there now? Stop the film and reflect for a moment. The only difference to the situation in A is that there is a 4th element that can be chosen from, namely, instead of John, Quentin, and Ramona, one can also leave the leaflet empty, which means we have 4 flavors, so n is just 4, and we get the result shown. Look now at task C, and again stop the film. So we have now 5 elements we're choosing from: John, Quentin, Ramona, empty, and rejected, which means n is 5, the k is still 25, and so we get the result that you see here. The number in the end is now 23,000 and something compared to the originally 351, so it has increased enormously by having increased the number of elements to choose from 3 to 5.